This is Mrs. O'Neill for Chapter 5, Section 2, Part 2, the electron configuration. So remember, there were three ways to show the address of these electrons. We talked about that orbital filling diagram in the previous video, and now I'm going to describe to you how we're going to write the electron configuration and its shorthand as well. So the electron configuration, pause the video, fill in the blanks, remember to read as you write. The electron configuration, again, is that arrangement of elements, and it's represented by three things. A big number, I call it, and that's going to be the energy level, the letter, which is going to correspond to the shape, the SP, D, or F, and that exponent really just gives us the number of electrons. And of course, in every orbital, there's a maximum of number, right? So S can only have 2 electrons, P can only have 6, D can only have 10, and F only 14. So we're going to use the diagonal rule, it's called, as a guide, and we're going to follow the arrows because the arrows follow the energy. So that's really how it goes. So let's look at this diagonal rule. First of all, the first energy level is only going to have one sublevel, the S. Second energy level is going to have 2, the S and the P. Third energy level is going to have the SP and D. See the pattern? And you already know this information even from 2 sections ago, I do believe. The fourth energy level then is going to have 4 sublevels. And then, yes, the fifth energy level technically has this G, which again hasn't been an issue yet. So I'm going to explain to you where that's going to come from. The 6 is going to have 6 sublevels. The 7 is going to have 7 sublevels. So we have energy levels, we have these sublevels, and the number above here is the maximum number of electrons. Those exponents are the maximum number of electrons that particular sublevel can have. So we're going to follow the arrows. So we're going to do an arrow down, an arrow down, an arrow down. That's the energy. That's the order of the energy. So that, gets filled up, that gets filled up, this gets filled up. That makes sense. The 3p, there's that little weird guy, right? The 4s before the 3d, 4p, 5s. Then it's going to be the 4d, the 5p, the 6s. So again, this is giving us the order of energy as well. So if we look here, I'm going to call those the blue sublevels. They're actually not occupied yet because there's not enough electrons. Now, even with these man-made electrons, not sure if they're really certain that those electrons, because those man-made elements live for such a short amount of time, they're really not sure what's going on there. So we're going to propose, or again, the theory is those electrons really do exist. Those sublevels exist, especially because we know that electrons get excited. So if we have those electrons in the 7p6 orbital, technically they should be able to jump to the 5g18 orbital. But again, we're not 100% what's going on there. But they're there, especially for those really, really large atoms. So let's get to those examples. Again, pause the video if you do not have your periodic table out yet, so that you're able to locate the element and find those number of electrons that are needed. So let's look at phosphorus. Again, where is it? Excuse me, on the periodic table. Hopefully you found it there. That gives us 15 electrons. So what's going to happen is I'm going to show you the orbital filling diagram first, just to show you how it relates again to that electron configuration. Then we're going to use that diagonal rule and actually write the electron configuration. So again, here's our energy orbital diagram. We're going to put those first electrons into the 1s. There we go. Again, opposite spin. Notice that opposite spin. Talked before I showed you. So the first part of the electron configuration is that 1s2. Well, 15 electrons we started minus the 2 that are now in the 1s2 orbital gives us 13 more. Here we go. So we're going to put the next 2 electrons in the 2s. That gives us that configuration, but we have 11 more electrons to go. So how about the 2p? All right, those are all filled. So again, that becomes our electron configuration. Still got 5 more to go. So we're going to put 2 more in the S3s spot. Again, add that to our electron configuration. And we got 3 more to go. Now, think about that. Where are those 3 going to go? What's the next part of the orbital filling diagram? What's the next energy? And where are those 3 electrons going to go? Hopefully, you know that they go in the 3p, but where's the next one going to go? Hopefully, you knew that's going to go here and here. So there are 3 electrons that occupy in the 3p subshell or suborbital, but they are separate. So we have 1s2, 2s2, 2p6, 3s2, and 3p3. Again, 6 is the maximum, but there's only 3 in there. So those are going to be considered unpaired electrons, and that's going to be important when we get to bonding. How many unpaired electrons are there going to be? How many available bonds are we going to be able to have? So the diagonal rule is what I just showed you, right? And so again, here just shows you the arrows, where to start and the direction. So the 1s2 gets filled first, then it's going to be the 2s2, the 2p6, the 3s2, and of course the 3p6 is next, but it's the 3p3 only because there's only 3 electrons available. So if we notice here 15 electrons, let's count. 2 plus 2 is 4, plus 6 gives me 10, plus 2 is 12, and plus 3 is 15 electrons total. So if we look at oxygen, you had oxygen when we did the orbital filling diagram. So if we look at that orbital filling diagram, it has 8 electrons. 2 are going to go in the 1s, then 2 are going to go in the 2s, and then we have 2p, and we're only going to have 4 more electrons. And remember, 1 in each before we start pairing up. So what's that electron configuration going to be? The 1s2, the 2s2, and the 2p4. So this shows the orbital filling diagram. It just gives it, I want to say that this is more specific, right? Where those electrons are, showing you the spin, showing you the orbitals, how many there are. And the electron configuration is just going to be straight up writing the energy, how they're filled up, the energy level, the sublevel, and how many electrons are in there. So for the shorthand, this is really easy, except again, there's always those tricks of the trade, or I want to say exceptions to the rule. So we're going to use that periodic table and find its location. Then the shorthand just means if there's a noble gas in front of that element, we're going to substitute that 1s2, the 2s2, the 2p6. We're going to substitute that beginning part of the electron configuration, just so we're not writing out the, I don't know, maybe an electron configuration that's going to take the, the whole page front and back. So we're going to shorten it up by writing just that noble gas that's before that element. Then the rest of it is the same. So it depends on what's left over. So this is where it gets a little tricky. The S and the P sublevels correspond to the energy level. And actually those S and Ps are going to give us those valence electrons. Again, something that's going to be really important later when we talk about bonding. But when we get to the D sublevel area, we're actually going to subtract one energy level. Again, remember energy level is that period in the period or row of the periodic table. And the F sublevel, we're actually going to minus 2. Okay, so what does that mean? So here's our periodic table, and you do have one in your notes. So you want to maybe, it's up to you if you want to shade them in, or just make sure that your groups 1 and 2 are the S level. Your groups, I don't like how they wrote it here, but this really should be groups 13 through 18 are the P level. Here is the D level, and that's your groups 3 through 12. And your F levels are those 2 rows on the very, very bottom. So what's going to happen is your S and your P do correspond to the period number equals energy level. But when we get to the D, this SC really is going to be 3D1, 3D2, 3D3. And in the F area, this LA, this lanthanum, is really going to be, remember, it's part of the period 6 here. So this is really going to be 4F1, 4F2. And again, I'm going to show you some more here. So here we go. We have the S's, the P's, and here's your D's, right? This is what they call either a D block or the D area. So notice the D area is 1 minus the period number, and in the F area is going to be minus 2. So remember that the periodic table really does look like this. So here's your S, here's your P, your D is going to be energy level. Remember that principal quantum number sometimes is represented by N. So this is going to be your row number, your period number, or your energy level number -1. And here in the F area is going to be -2. So again, just to show you what those electrons are going to look like, again, here we have 1s1, this is going to be 1s2. Then we get to the 2s1 and 2. Here we get to the p section, 1, 2, 3, 4, 5, and 6. Again, the 3s is going to be 1 and 2. The p sections are going to be up to 6 electrons. Now that we get to the 3D, again, now this is going to start 1 through how many? You know this, right? Up to 10, so that should make sense. And of course, your the P's are going to be 1 through 6. And your F sublevel down here, again, is going to be 1 through how many? You should know this by now because of the charts and what we've talked about, but those are going to be up to 14 electrons. So now let's look at some of these examples. Again, have your periodic table out. So sulfur again, locate sulfur and find how many electrons there are. Hope you found that it's 16 electrons. So let's fill them up using that diagonal rule. Again, you have one in your notes, so please use it as a guide. So 1s2, 2s2, 2p6, and 3s2 is going to be your full electron. Oops, sorry, 3p4. I should have counted my electrons, right? 2 plus 2, 4 and 6 make 10, plus 2 is 12, plus 4 is 16. Sorry about that. And we want to remind you that these are actually called the core electrons, and these are called the valence. Again, the valence are going to be really important when we talk about bonding. So if we want to write this the shorthand way, well, again, if you look at sulfur, the noble gas before sulfur is Ne. So we're going to, oh, I forgot I showed this to you. So again, here's our sulfur. We're going to write that noble gas ahead of time, which is Ne. Then we're going to finish the electron configuration. So 3s2, and what's left here? P, 1, 2, 3, 4, and it's going to be the 3p4. So we have our noble gas, and then what's left over. And again, knowing where or what parts of the periodic table are what, it's real easy to kind of fill in those blanks. So sulfurs, again, full configuration is here, and your shorthand electron configuration is there. And yes, you need to be able to do all three things: the orbital filling diagram, the full electron configuration, and if it just says electron configuration, it is the full. The only time you can use the shorthand is if it specifies shorthand. All right, so do we see a pattern? Isn't this pretty neat? When we talk about valence electrons, we can go up to 8 valence electrons. So if we look at group 2, how many total electrons are in there? 2. Woohoo! So we're actually going to learn that there's going to be a nice pattern. And if we look at group 18, has 8 valence electrons. Well, where do they come from? Again, 2 plus 6 total is going to be 8. So let's do another example of zirconium. Again, locate that on your periodic table. You should have found it there in the D area. Uh-oh, that's a big, little light bulb should be going off. So we're going to, so that's 40 electrons. We're going to highlight the noble gas before it, and that's going to be krypton. Then we're going to finish the electron configuration. So 5s2, and then the 4d2. You got it. 4d2, is that right? Yep, 4d2. I might have, sorry about that. This should be over 1. But it should be 4d2. So apologize for that. So can you go the other way? Of course you can. We've been doing that, right? If I give you the electron configuration, you just count those electrons, find that atomic number, and boom, give the element. So what's the element? Count those electrons. 2 plus 2 plus 6, 10 plus 2, 12 plus 2 is 14 electrons on your periodic table. The atomic number 14 gives us the element of silicon. So one more I believe I have. So count those electrons up. You should have gotten, should have gotten 26. And so 26 on your periodic table is iron. So this is a different end, I'm going to say. This is your end that I always put the picture of. I'm going to let this run. Hopefully it doesn't go past my time frame here, but I thought this was pretty neat. It's showing you the elements, and it's showing you those electrons and how they're filling up. So I'm just going to kind of let this run until it stops.